So let us remember what is it that we were doing before the exam break, right? We took a discrete system with a finite number of degrees of freedom, and we just, we defined a continuum limit of this finite number of degrees of freedom, so that we could, generate a continuous system. So that's how we went from this Lagrangian here with n degrees of freedom to this Lagrangian here in terms of a continuous index. This index I here, discrete, has become now the index x continuum. And that's how we are going to understand fields. So a field is going to be a function of x, and that's going to be the continuum limit of, a q sub I in the old version of the Lagrangian dynamics, right? So a field is going to be the continuum version of a discrete system. And from this Lagrangian, in this particular case, we saw that, the equations of motion corresponding to the Lagrangian were these ones. But of course, we want to do other situations, not just this system of, an infinite set of what was it, of springs, right? I think it was springs, right? So we want to also, describe any other field theory, not just this one. So we need a principle, we need a method that would allow us to go from the Lagrangian, or from the action, to the equations of motion. And so that is going to be, again, okay, the principle of a stationary action. Stationary action, known as Hamilton principle. So that's Hamilton's principle, right? Hamilton's principle. So we want to repeat now in terms of these functions q of x and t, so-called fields, something that is going to be very similar to the principle of a stationary action that was the guiding principle that would lead us from the action to the equations of motion, right? So let's start doing that. So this is going to be the Lagrangian formulation of continuous systems. Okay. All right. So the idea is, just for simplicity, we're going to generalize this thing very soon, but just for simplicity, we're going to take a one-dimensional case. The generalization is going to be obvious, okay? And we see that we have, for instance, a Lagrangian, by the way, a Lagrangian density. Remember that what we find is that the Lagrangian is now the integral. So maybe we should say this thing here. So let me say it, okay? I'm going to say it explicitly. So the Lagrangian now has become the integral over x from x1 to x2 of something else, which is going to be a function of the fields and derivatives of the fields. Could be the time derivative, the space derivative. So the space derivative, the time derivative. And in this case, it doesn't happen, but it could also happen that it depends explicitly on x and t, because I mean, we're integrating over x, so therefore this whole thing could depend explicitly on x and t. So this L is still the Lagrangian. So this is what is called the Lagrangian. And this curly L, so calligraphic L, is the density of that quantity. So it's the Lagrangian density. Lagrangian density, okay? And as you can see here, the thing that is going to play the main role is not going to be the Lagrangian as it was, in the case of discrete systems, but this main role is going to be replaced by the Lagrangian density. Now the Lagrangian density is going to be the main object here. And it's so much, the main object that, in practice, people forget about the density part and they call this thing the Lagrangian. Although strictly speaking, they should call it the Lagrangian density because the Lagrangian is this other thing, right? But in practice, people call this, calligraphical, the Lagrangian, and they forget about the density part. So in some cases, we will also do that, okay? But it should be clear what we are referring to. So this is going to be the Lagrangian density in this case, okay? So this is going to be a function of our field, Q of x and t, and derivatives of this field with respect to the two variables that it depends on, which is the space and also time. And in general, there could also be an explicit x and time dependence here, okay? Although this is very strange, okay? This doesn't happen very often. So here, I'm just, really going, more general than actually is going to be needed in practice. But let's keep it in here just just as an example, okay? Now, Hamilton's principle we know what it is, right? It says that the variation of the action has to be 0. And this is going to lead to the equations of motion. So let's do the same. Let's do the same, okay? And is the variation under what? So it's the variation means that we're going to take, each field, in this case, Q of x and t, and we are going to generalize it with a parameter alpha, which actually takes a variation with an arbitrary function from the stationary value. The stationary value, which means the solution to the equations of motion. So that's exactly the same as what we did for discrete systems, okay? Now, this eta of x and t is going to be an arbitrary function. Of course, sufficiently smooth, means, continuous and with infinite derivatives, infinite continuous derivatives, okay? And with some boundary conditions. And the boundary conditions, are going to be the same as in the case of the discrete version of this thing, which is that eta of x1 and x2 for all t, I don't know why I put here a colon, so this should be a comma. For all t is going to vanish, and then eta for all t1 and t2 is also going to vanish. So this variation, this arbitrary function eta, is such that it vanishes at both ends, both in space and in time. At both ends, both in space and in time. So the action, which is, as always, the integral with respect to time from t1 to t2 of the Lagrangian, now it becomes the integral from t1 to t2 and the integral from x1 to x2 of the Lagrangian density, of this Lagrangian density, which I'm going to write again with all the details, even though in practice, the xt dependence here and here, usually is forgotten, okay? People do not put it. But since it's the first time, let's put everything in it, okay? So that's the action that we want. And after we make this replacement in terms of this parameter alpha, now what we want is we want to take the derivative of s with respect to this parameter alpha and equate that to 0, okay? So that's what we want. All right, so let's do that. So what is it going to be the derivative of s with respect to alpha? So that's going to be the integral from t1 to t2 of the integral from x1 to x2 dt dx of, and now we have to start taking derivatives. Okay, so that's the derivative of the Lagrangian density with respect to q, derivative of q respect to alpha, plus derivative of the Lagrangian density with respect to derivative of q respect to t, derivative with respect to alpha of the derivative of q with respect to, actually, if you wish, since q depends on x and t, we're going to put dq dt. And this is going to be derivative of q with respect to t. Remember that q depends on x and t, plus the derivative of L with respect to the derivative of q with respect to x now, derivative with respect to alpha of the derivative of q with respect to x. So that's all there is. So that's the derivative of s with respect to alpha. But remember that alpha does not depend on x or t, right? It's a completely different parameter. So taking the derivative of this q with respect to x or t, it commutes with the derivative with respect to alpha, because alpha does not depend on x and t. So that means that the derivative with respect to alpha of the derivative of q with respect to t is going to be the same as the derivative with respect to t of the derivative of q with respect to alpha. Okay, and this is also true. It's also true for x. So derivative with respect to alpha of the derivative of q with respect to x is the derivative with respect to x of the derivative of q with respect to alpha. Okay. Okay, so let's do one of them because the other one is going to be a repetition of this. So now we have the integral with respect to t from t1 to t2, okay, of the derivative of the Lagrangian density with respect to derivative of q with respect to t, derivative with respect to alpha of the derivative of q with respect to t. So I'm treating this first term, okay? And what I do is exactly what we did in the case of discrete systems again. It's the same strategy. So we just commute these two derivatives. So that's going to be derivative integral from t1 to t2 of the derivative of L with respect to the derivative of q with respect to t. And now this is the derivative with respect to t of the derivative of q with respect to alpha. And we integrate by parts. Okay, so integrating this thing by parts, this becomes the integral dt. So let me just do it on the next line. Equals integral dt from t1 to t2. And this is the derivative with respect to t of everything, which is the derivative of L with respect to the derivative of q with respect to t, times derivative of q with respect to alpha, minus the integral dt from t1 to t2 of the derivative with respect to t of the derivative of L with respect to the derivative of q with respect to t, times derivative of q with respect to alpha. Right? So do you guys follow? Do you agree with me? There is this minus sign here. Any questions so far on, regarding these manipulations?
No.
Okay. All right. If there is anything, you just slow me down. Huh? I mean, just ask me whatever you want. So let us look at this first term. And here, what is going to happen, we can already foresee that what is going to happen is what already happened, in a discrete system, because this thing here is going to be, this thing in the square brackets evaluated at the upper end minus the same thing evaluated at the lower end, right? So this is going to be derivative of L with respect to derivative of q with respect to t. Derivative of q with respect to alpha is eta, right? Eta of x and t. That's what it is, right? And this evaluated at t2 minus at t1. But of course, remember the boundary conditions for this arbitrary function eta, right? It vanishes at both ends in time and also in a space. And now it's time that matters, so this thing here is 0. So this term is 0. And the same thing happens for t going to x. So we can repeat the same thing for x, okay? And it's going to be the same. So all in all, what happens is that this term becomes minus this term, and this term is also going to become minus the same thing, you know, exchanging t and x. Okay, so that means that derivative of s with respect, oops. Derivative of s with respect to alpha, which is 0, that's the principle, is the integral dt from t1 to t2, integral dx from x1 to x2. And what do we have? First term is dl dq. So dl dq. Sorry. Next term is this thing with a minus sign, okay? So this minus d dt partial of L with respect to partial of Q with respect to T. And then the same thing with X, d dx partial of L with respect to partial of Q with respect to X. And this whole thing multiplied by dq d alpha. dq d alpha, which is nothing but eta of x and t, right? Eta of x and t. Now, again, remember that theorem of the calculus of variations. That says that if this integral for an arbitrary function eta sufficiently smooth, sufficiently differentiable, okay? Maybe instead of a smooth, we should say differentiable, right? Sufficiently smooth. I say differentiable. It's more technically accurate. So if this thing with an eta sufficiently differentiable equals 0, then this means that the integrand is 0. So dl dq minus d dt partial of L with respect to, with respect to dq dt minus d dx partial of L with respect to dq dx. This has to be 0 now. Okay, so that's going to be the new Euler Lagrange equations of motion for fields. So that's how a field is defined. So you give me an action. The action is going to be the integral over t and x of the Lagrangian density. And then from the Lagrangian density, we just take all these derivatives, okay? And that leads to the equations of motion, okay? Now, we have to pause and reflect a little bit what this means and whether this works, right? Because now we have to apply it to our case, to the infinite set of springs that we had, for which we took the continuum limit, and we have to verify that exactly this equation, you know, reproduces the result that we had in that case, right? That we had in that case. Okay, so let's pause 1 second here and see whether there are any comments or questions, because this is going to be the fundamental equation. Huh? This equation here is going to be the battle horse of classical field theory, or one of the battle horses.
Santi, I'd like to ask a question.
Okay.
When you integrate by parts,
Yes.
can you go to that slide?
Yeah. Here.
When you split the two integrals, you make total derivatives respect to time.
Yes.
Why is not a partial derivative?
Because you know this is going to be all the time derivative that we have, right? That's how, you know, what is the integration by parts rule here, right? What is it? I mean, here we are saying that this is the time derivative. Let me just put it in another way. Let's see whether, let me just do a little calculation here. If I do d dt of f of q xt and t, right? If I do this, what I mean is partial of f with respect to q, partial of q with respect to t. And this is partial, and there is another term. Huh? This is partial because q depends on x and t. And then I have partial of f with respect to t, right? Okay. So this is what, you know, a partial derivative means. And it's not the same as this, because in this derivative, I'm only taking the derivative with respect to this variable. Right? So the integration by parts says that, you know, I have to do this. This is what I have to do. You know, here I have to take the derivative of everything.
Okay. Okay. Okay,
Right?
thank you.
Okay, so let's take this out. Okay, now, several things. I mean, by the way, any other question or comment? Good. Now, remember that we started from a Lagrangian that has some x and t explicit dependence, right? We just said, you know, we want the most general thing, even though this thing is not very common. It doesn't happen very often. I mean, there are only a few cases in which you have to consider these explicit dependence. Most of the time, the Lagrangian density will depend on the field and derivatives of the field, okay? So, but in this case, we consider this thing. And this is why, in particular, here we have to be careful. And we are taking the total derivative with respect to time and x. So your question was actually very pertinent, right? Because now we'll have to be careful about this. If this Lagrangian has this explicit this explicit x and t dependence, then it makes a difference whether this is the total derivative or is the partial derivatives, right? So this is because we have a Lagrangian which depends on q of x and t, partial of q with respect to t of x and t, and partial of q with respect to x of x and t. X and t is because we have this dependence here that this thing is not the same as the partial derivative with respect to t. Okay, this is the reason. So let's add this thing here. However, if, as happens most often, as let's say it explicitly, as happens most often, the Lagrangian density is just a function of the fields and derivatives of the fields only. So this time derivative and this space derivative, but there is no x and t, then what difference does it make whether I take the total derivative with respect to time here or the partial derivative with respect to time? Because, you know, when I take the total derivative with respect to time, of course, I'm taking the derivative with respect to this time dependence, this, and also this time dependence. But if there is no time dependence here, then this total derivative and this total derivative becomes partial derivatives. So in this particular case, which is what happens most of the time, then the equations become partial of L with respect to Q minus derivative with respect to T, partial of L with respect to dq dt, minus derivative with respect to x, partial of L with respect to dq dx equals 0. And this is probably the formula that you guys are going to see in most books. And the reason is because in most books, they already go for the typical case in which there is no explicit X or T dependence, okay? So don't get confused, okay? Most of the times, you're gonna be able to use this form, but sometimes if there is some X and T dependence, you have to be a little bit extra careful. So is this clear?
Yes.
Okay.
Well, Santi.
Yes.
One question about what the previous student asked and about what Eric asked. And when you do the chain rule, if
Yes.
it's a total derivative, and then you have to do the partial, but then the second one, the second term, it's also a total derivative, no? I mean.
Yes. So let's take this thing here.
Yeah, exactly.
Okay. So you're saying, if I take, I mean, this thing plus this thing should be the previous term, because I'm saying that they are the same, they are equal, right? So let's take this derivative here, okay? If I take this derivative here, you agree with me that the first term is going to be the total derivative of the first term times the second.
Yeah. Sí.
And that is going to cancel this guy.
Yeah, sí.
Okay? But there is another term, which is this partial derivative of L with respect to dq dt, and then the total derivative of dq d alpha.
Yeah.
Okay? Now, what difference is there between the total derivative with respect to t of dq d alpha and the partial derivative with respect to t of dq d alpha?
Well, the derivative respect to x, I mean the partial derivative of.
Let's do it here. Let's do it here. Let's do this. This is what is called a back of the envelope calculation. So let's do a back of the envelope calculation. So we're trying to see whether d dt partial of q with respect to alpha is the same or not as d dt partial of q with respect to alpha. Right? Do you agree with me that that's the thing that we're trying to figure out? Huh?
Yeah, exactly.
Okay. So what is dq d alpha? So let's go step by step and let's make this thing clear once and for all. What is dq d alpha? We go back. dq d alpha is eta, right? Is this function eta, right?
Yep.
So this is d dt eta of x and t. Okay? Now, does x depend on t? Yes or no?
Well, no, yeah.
It does not depend on t. X is just another variable like t. I mean, in discrete systems, when we were discussing discrete systems, the variable was usually called x. Well, sometimes it was called q, right? But sometimes it was called x. And back then, when the variable was called x, the dynamical variable was called x, then x was depending on t, on time. That was the solution to the question of motion.
Okay, I see, yeah.
But now it doesn't. Now x is an index. X replaces I, the index I that goes from 1 to n, except that now it's continuous. So x does not depend on t. And if x does not depend on t, this derivative and this derivative are exactly the same. Right?
Yeah, I see. I see.
Okay.
Thank
now, any other question or comment about this thing? But I'm going to leave it here. So I hope that nobody gets confused, that this is just a side remark. I'm going to leave it on the screen, okay? So where were we? Yeah, so we were here. Okay, so as I was saying, most of the time I'm going to use this just the usual notation, in which we just take partial derivatives. But be careful if the Lagrangian has explicit x and time dependence, okay? Now, several things we're going to say. Well, I mean, taking the derivative of L with respect to the derivative of Q with respect to time, this is a little bit cumbersome, right? It's just too many derivatives of Q. That's too much, okay? So most of the time, people are going to do that. I mean, for dq dt, they can talk about Q dot. That would be also okay. So that would be the derivative with respect to time. But, you know, in the context of field theory, what people talk about is Q comma 0. And 0 because time is soon going to be the 0th component of a tetra vector, a 4 vector in relativity, right? So most of the time, people talk about the derivative of Q with respect to t as Q comma 0, and therefore this is going to be dl dq comma 0. And the same thing with the space. So this notation is just too many things, okay? Then people replace the dq dx by q comma x, okay? So this is going to be dl dq comma x. All right? So we're going to follow this notation because it's very convenient. Otherwise, there are too many symbols here. So that's one thing. So that's one thing that we have to remember, okay? Then the equations, so let's write them like this. Then it's going to be dl dq minus d dt dl dq comma 0 minus d dx dl dq comma x equals 0. So that's the Euler Lagrangian equations of motion. Equations of motion. Now, okay? Now, good. So that was a relatively trivial observation. Okay, but now we can do other things, right? We can do other things. Let us look back at the action. So the action was integral dt from t1 to t2, integral dx from x1 to x2 of the Lagrangian density. Well, this is the integral dt dx of the Lagrangian density over the whole space and time, over the whole volume in time and space, right? Now, the point that I want to make now is that this formulation is naturally, you know, incorporating the possibility to make the theory relativistically invariant. It's very natural that, you know, relativistic theories are going to be expressed in this form just because this object here is an invariant volume in Minkowski space, in the space of time and real space, right? So this is prepared. So this formulation accepts, let's say it like this, accepts naturally relative, right? Without any effort. I mean, it's very natural in it. I mean, of course, the fact that, you know, the action is written as an integral over the whole time and space volume of the Lagrangian density, that fact doesn't make, you know, all theories relativistically invariant. This is clear, right? I mean, this is one piece, which is relativistically invariant, but, you know, that doesn't make the whole action relativistically invariant. So what is the extra, you know, condition that we need to make the whole theory relativistically invariant? What do you guys think? I mean, it cannot be that all theories, you know, that I can write down just because I have this volume here are going to be now relativistically invariant. This is not true. I mean, I mean, this formulation can also be used to describe, you know, the water in you know, that goes through my faucet in my home. Okay, and this is not relativistically invariant. So what is the extra condition that I need to really make my theory fully relativistically invariant?
The Lagrangian density has to be relativistically invariant.
Exactly, yes. The theory will be relativistic if L is relativistic. Right? So, I mean, we need a Lagrangian that is relativistically invariant. Then the whole formalism is prepared to make, you know, everything relativistically invariant if the Lagrangian is relativistically invariant. Okay, so that's one thing. And so most of the theories that we are going to look at will be relativistic, okay? Among other things, because relativity is a symmetry of nature, right? So nature is relativistic. Well, that's one thing. Then another thing is that, as in the case of discrete systems, L is not unique, right? So we, in the case of discrete systems, it was the truly Lagrangian the true Lagrangian, not the Lagrangian density. But now we can say the Lagrangian density is not unique. So why is it not unique? Unique means that, you know, there are several Lagrangians. So several Lagrangian densities lead to the same equations of motion, right? So let's see, you know, what difference do they have among them, right? So let's see. So we have a Lagrangian, okay? And if I change this Lagrangian into another Lagrangian, how do I make sure that the new Lagrangian is going to have exactly the same equations of motion? For instance, what can I do to this Lagrangian to assure that?
Multiplied by a constant.
For instance, absolutely. So if I multiply by a constant, the equations of motion are not going to change. But is that all I can do to a Lagrangian to ensure the same equations of motion?
You can add total derivatives respect to time and x of functions.
A total derivative with respect to time of
A function
a
depends
function
on q, x, and t.
which depends on q, absolutely. So q now is the variable, x and t.
And same with another function, but for x.
Aha, very good. Yes, absolutely. Another function now, which depends on x, q of x and t, x and t. And the reason is because this function here is not going to modify the stationary principle for the same reason as what happened in the case of discrete systems. It's exactly the same story, right? Because this is a total derivative, so it's going to be this thing at the upper end minus at the lower end, and therefore these boundary terms, you know, cancel when I take variations, right? Is that clear to everyone?
Yes.
Okay, and now it happens both for time and space, because they play the same role, right? They are symmetric. The role they play is symmetric in the action, and is also symmetric in the equations of motion. It's all the same. It's just a repetition. Time and space now are on equal footing, we could say. They are now on equal footing. So this, we can immediately say, well, I mean, look, I'm going to define a derivative. I'm going to call it like this, d mu, and this is going to be a derivative with respect to time, comma, derivative with respect to space, x, okay? And if this is the case, then the above symmetry that I have, in which I can change the Lagrangian and I change nothing because the equations of motion are the same, is the Lagrangian goes to AL plus derivative of a function, omega mu, which I'm going to write as f of q, x, and t, and g of q, x, and t, x, and t. You see, so I'm basically cheating here. So I'm cheating because I'm writing something which is not relativistically invariant, a notation which looks relativistically invariant, right? And the reason why I do that is because I'm already preparing the situation in which the Lagrangian will be relativistically invariant. And you see that, you know, everything happens as if, you know, it was relativistic, okay? Again, if the Lagrangian density is not relativistic, the whole theory is not relativistic. Even if I write this d mu like this, okay? Or omega mu like that, okay? Where mu is 0 and 1. Right in here, because I have only two components, time and space, and one coordinate in space. Okay, but the whole formalism is prepared for relativity. Okay, good. Now we have to do the example. So we already derived the Euler-Lagrange equations of motion for the string, right? For a string, and we know that the Lagrangian density for the string was 1/2 of mu, which was the mass density, dq dt. So let me just write it like this, dq dt squared minus Young's modulus, remember, dq dx squared. And we want to apply Euler-Lagrange equations of motion, which is dl dq minus d dt dl dq comma 0 minus d dx dl dq comma x equals 0. And we have to see what equations result from that, right? So let's do it. So let's compute dl dq. What is this? How much is this derivative? 0, because the Lagrangian only depends on the derivatives of q, not on q itself. So this is 0, okay? So now, next, what is the derivative of L with respect to q comma 0? How much is this?
Mu q comma 0.
Right, mu q comma 0, mu dq dt.
Yeah.
Okay. What is dl dq comma x? Well, it is minus Young's modulus dq dx. Right? And so, Euler-Lagrange equations of motion are time derivative of this plus space derivative of this equals 0. So that is mu dq squared respect to dt minus y dq dx equals 0. Ah, perfect. So that's exactly right. That's the equations of motion for the string. Remember? Right? It was a wave equation, right? We can just go back. Here it is, right? So we got it right. So the principle reproduces, the principle of stationary action reproduces the equations of motion that we expect. Okay, so this is good. Now, so that's page 100. So that means that I have to change notebooks. Okay, so I'm going to change notebooks. Any questions at this point?
No.
Okay. So we start with a new notebook, and we're going to make a change of notation. because nobody talks about Q of X and T. People don't talk about this. I mean, this is the, the notation that we have been using so far, because Q, this Q of X, is reminiscent. It comes from the Q sub I that we had in the discrete system when we took the continuum limit, right? But when talking about fields, this Q of X and T becomes usually phi. So people talk about phi, and phi, not just one variable, but it could be phi of X and T, right? Because the space has 3 coordinates, okay? So people talk about phi of X and T, so not Q. So now phi is going to be the dynamical variable, okay? And the field phi of X and T could be a function as we see here, but it could be a vector also, in which case, okay, it could have several components. It could be a vector with several components, in which case we could just, call it A mu. I'm going to just put the index, and it's going to be a function of X and T. And this is going to be A0 of X and T, A1 of X and T, A2 of X and T, and A3 of X and T. And that's actually what happens. This is what happens in electromagnetism. Electromagnetism. Or it could be, or the field could be a tensor, which means an object that has not just one index, but more than one index. Like, for instance, 2 indices, and this could be G mu of X and T, in which mu and nu would take value 0, 1, 2, 3, for instance. And this would be, this is what happens in general relativity, for instance, general relativity, okay? So the field itself could have an index, right? The field could have an index, and this index alpha is an index. And sometimes this index could be 1, could be 2, could be 4, could be whatever you have in the problem at hand, okay? And then, so say that, we have a field phi with an index, then the equations of motion are going to be dl d phi with that index minus d dt, derivative of L with respect to phi alpha comma 0 minus derivative with respect to x, derivative of phi with respect to phi alpha comma x. And if I have 3 components, then it's going to be xi equals 0. Right? So this I here is 1, 2, 3 space components. Right? Whereas alpha equals 1n is the components of phi, depending what field I have. I mean, I may have a field with 4 indices, or I may have a field with 300 indices. I don't know. Depends on the field. Depends on the theory that I'm looking at. Okay, so don't get confused with all those many indices, okay? Don't get confused.